People think quantum mechanics is weird because particles behave like waves. But that sentence is still too soft. It doesn't capture how deep the weirdness goes. Here's a sharper way to say it. In quantum mechanics, the universe doesn't choose one path and follow it. It adds up every possible path. Not as a metaphor, as a calculation rule. This is the idea behind Feynman's path integral, also called the Sum Over Histories. And if you understand this one concept, a lot of quantum physics suddenly looks less mysterious. It becomes mechanical, almost inevitable. Imagine you want to predict where a particle will be a moment from now. In classical physics, that's simple. You say, it has a position and a velocity, and it moves along one clear trajectory. One story, one route. Quantum physics refuses that simplicity. Quantum physics says the particle doesn't come with a single definite trajectory you can track like a car on a road. Instead, to compute what happens, you consider all the routes the particle could take. Every route contributes, every route carries a weight, and the final answer is what you get after you combine them all. That sounds impossible at first. All routes includes insane ones. Routes where the particle loops around, zigzags, teleports across the room and back, paths that look completely unphysical. But quantum mechanics does not ask whether a path is reasonable. It asks whether a path contributes. And here's the twist. Most of those crazy paths cancel out. They don't cancel because someone deletes them. They cancel because of interference. So the problem becomes this. If reality is built from all paths, why does the macroscopic world look like one path? Why do we still see classical trajectories? The path integral answers that too. It tells you that classical physics isn't wrong. Classical physics is what happens when a massive number of quantum possibilities interfere in such a way that only one family of paths survives. That's the real upgrade. Classical motion becomes an emergent pattern of quantum interference. Now the key question, how do you decide which paths contribute more and which contribute less? Feynman's answer is brutally elegant. Each path gets an amplitude. That amplitude has a phase, and the phase is determined by one quantity, the action. So the entire universe starts to look like a machine that assigns a phase to every possible history, then adds them all up and produces reality as an interference pattern. That's what we're going to unpack. To make this concrete, forget particles for a second and think about the most basic thing in physics, motion. Classically, if I throw a ball, it follows one path, a clean arc. If I roll a marble, it follows a smooth curve, a single trajectory. Quantum mechanics says, yes, that's what you see. But under the hood, the calculation doesn't use one path. It uses all paths. So how do we measure the contribution of each path? Feynman tells you to assign an amplitude proportional to x I times s over h bar. You don't need to love the formula yet. Just understand what it means. S is the action of the path. H is Planck's constant, the quantum scale. I means this is a phase in a complex amplitude. So a path doesn't get a probability. It gets a rotating arrow, a complex contribution. Its direction depends on the action. Now here's why classical physics emerges. When the action changes a lot between nearby paths, the phases twist rapidly. One path points this way, a slightly different path points the opposite way, another points sideways. When you add them all, they mostly cancel. But if there is a region where changing the path changes the action only a tiny bit, then nearby paths have almost the same phase. Their arrows point in nearly the same direction. They add up constructively instead of canceling. That region becomes dominant, and the path that sits at the center of that region is special. It is the path where the action is stationary, not necessarily minimum in every situation, but stationary. Small variations don't change it at first order. That's the classical path. So classical motion is not imposed from the outside, it is not a separate rule. It is the result of a quantum sum where only the stationary action neighborhood survives massive cancellation. This is one of the most beautiful unifications in physics. Classical mechanics becomes an approximation of quantum mechanics, and the bridge is simple. Classical path equals stationary action path. Quantum reality equals interference of all paths around it. This also tells you why quantum effects are easy to see in small systems and hard to see in big ones. Because the bigger the system, the larger the action becomes compared to h-bar. When S is huge, the phase rotates insanely fast for tiny path differences. cancellation becomes extreme. Only an incredibly narrow bundle around the classical path survives. That's why a baseball doesn't show interference in your backyard, but an electron does in a lab. Now we can finally connect this to something you've probably heard about: wave functions. The path integral isn't a different theory from the Schrödinger equation. It's another way of computing the same physics. It's like two languages describing the same structure. One language evolves a wave function forward in time. The other language adds up histories. And Feynman's language has a superpower. It makes certain problems easier and makes the why behind classical behavior more intuitive. Now let's push it into a famous experiment and watch it explain something that looks like magic. Go back to the double slit experiment. You fire electrons one by one at a barrier with two slits. You get an interference pattern. The standard story is the electron is a wave, but the path integral gives you a sharper picture. From the source to the screen, the electron can take infinitely many paths, but many of those paths pass through the region of the slits. So the amplitude at a point on the screen is the sum of contributions from paths that go through slit A and paths that go through slit B, plus all the tiny variations around those. Each family of paths has its own phase behavior. When you add them, you get constructive interference in some places and destructive interference in others. That's the interference pattern. Now here's where the path integral becomes terrifyingly clear about measurement. If you place a detector to find out which slit the electron went through, you are not just watching. You are changing the conditions of the sum. You are making the histories distinguishable. The electron's paths become entangled with the detector's states. The phase relationships that produced interference no longer combine in the same way. The cross terms vanish. Interference disappears. This isn't mystical, it's bookkeeping. The universe keeps track of information physically. So the path integral tells you something powerful. Quantum weirdness is not a random glitch. It's what happens when different histories remain allowed to interfere. And classical certainty is what happens when those histories are forced apart by environment, information, and decoherence. Now, path integrals also explain something you've likely heard but never felt: quantum tunneling. Classically, if a ball doesn't have enough energy to climb over a hill, it can't get to the other side. End of story. Quantum mechanically, there are paths that go through the hill. They are not classical paths. They do not follow the classical energy rule at every point. But in the sum over histories, they contribute. Most cancel, but not all. The result is a small but non-zero probability of appearing on the other side. That's tunneling. And tunneling isn't a special extra law. It's a natural consequence of the path integral structure. Now, one more mindbender. The trick that makes tunneling calculations possible is to change time itself. Physicists perform a move called Wick rotation, where you shift real time into imaginary time. When you do that, the oscillating phases become exponential weights. The cancellation picture becomes a least action picture, and rare processes become easier to compute. You don't need the math here. You just need the feeling. The same formalism can be transformed to reveal hidden pathways in probability. Now we're ready for the final part: what the path integral really means, what it does not mean, and how it connects to Feynman diagrams. The path integral is often misunderstood as a literal claim that the particle physically takes every possible path. That's not the safest way to say it. A better way is, to predict outcomes, quantum mechanics assigns an amplitude to every possible history consistent with the boundary conditions, and the observable probability comes from the interference of those amplitudes. It's a calculation rule that produces experimentally correct results. Whether you want to interpret those histories as real is where interpretations begin, and that's a separate conversation. Now here's the part where everything connects back to Feynman diagrams. In quantum field theory, particles can be created and destroyed. Histories aren't just paths in space, they're full space-time interaction patterns. When you do the path integral over fields, you end up expanding the result as a series, and that series can be organized into pictures, diagrams. That's what a Feynman diagram really is, a term in the expansion of the path integral. This is why the diagrams feel like they're showing what happened, because they are snapshots of interaction structure inside the sum over histories. So the path integral is the deep engine, and the diagrams are the organized outputs. Now let's end with the biggest insight. Feynman didn't just invent a trick, he gave physics a different worldview. Reality is not always a single story. Reality is an interference pattern of possible stories. Classical life feels like a single narrative because the environment crushes interference. Decoherence forces histories to separate. Big actions compared to H-bar create violent cancellation everywhere except near the classical path. But at the microscopic scale, where H-bar is not negligible, the universe reveals its real operating system. Not one path, all paths, weighted by action, combined by interference. And that isn't poetry, it's machinery. So when someone tells you quantum mechanics is random or mystical, remember this: it's not magic, it's accounting. The universe adds arrows. Most cancel, a few survive. And what survives is what you call reality. If you enjoyed this, the next natural episode is the one that turns this idea into a practical tool: Feynman diagrams. Because once you accept sum over histories, the diagrams stop looking like art and start looking like code.